Okay, so I'm gonna start cell respiration. Now, the key concepts in cell respiration is to understand the catabolic pathways and that they yield energy by oxidizing organic fuel. Glycolysis harvests chemical energy by oxidizing glucose to pyruvate. Now, after pyruvate is oxidized, the citric acid cycle completes the energy yielding oxidation of organic molecules. Now, during oxidative phosphorylation, chemiosmosis couples electron transport to ATP synthesis. Oops. Fermentation of anaerobic respiration enables cells to produce ATP without the use of oxygen. Glycolysis and citric acid cycle connect to many other metabolic pathways. Why is this thing so weird? Now, study tip. Draw a cell with a large mitochondrion, labeling the parts of the mitochondrion. As you go through this chapter, add key reactions for each stage of cellular respiration, linking the stages together. Label the carbon molecules with the most energy and the carbon molecules with the least energy. Your cell can be a simple sketch. Now, mastering biology, etc., etc. Sorry, Marmota garigata obtains energy for its cells by feeding on plants. In the process of cellular respiration, mitochondria and the cells of animals and plants and other organisms break down organic molecules generating ATP. Let me just verify if there's any exclusions. Now, how is the chemical energy stored in food used to generate ATP, the molecule that drives most cellular work? Now, light through photosynthesis generates organic molecules and oxygen. These organic molecules and oxygen are used in cellular respiration in mitochondria. Then this generates CO2, H2O, blah blah blah. Now, catabolic pathways yield energy by oxidizing organic fuel. This is good. There's something wrong with this. Is it like too small or too large? Okay. Living cells require transfusions of energy from outside sources. to perform their many. For example, assembling polymers, pumping substances across membranes, moving and producing. The outside source of energy is food. The energy stored in the organic molecules of food ultimately comes from the sun. It's too big. 2.7. Energy flows into an ecosystem as sunlight and exists as heat. In contrast, the chemical elements essential to life are recycled. Photosynthesis generates oxygen as well as organic molecules used by the mitochondria of eukaryotes as fuel for cellular respiration. Respiration breaks this fuel down, etc. Now, breaks down this fuel using oxygen, generating AT. Still something wrong with this. Let me fix it. Here. Let's consider how cells harvest the chemical energy stored in organic molecules and use it to generate ATP, the molecule that drives most cellular work. Metabolic pathways that release stored energy by breaking down complex molecules are called catabolic pathways. Okay. Still something wrong with it. This is transfer of electrons from food molecules like glucose to other molecules plays a major role in these pathways. In this section, which are central. Okay, catabolic. Catabolic pathways and production of ATP. Organic compounds possess potential energy as a result of the arrangement of electrons in the bonds between their atoms. So the potential energy is a result of the arrangement of electrons in the bonds. Why is it big? Or something's wrong with the zoom? Compounds that participate in exergonic reactions can act as fuels. Throughout the activity of enzymes, a cell systematically degrades complex organic molecules that are rich in potential energy to simpler waste products that have less energy. Some of the energy taken out of chemical storage can be used to do work, which is the objective. The rest is dissipated as heat. One catabolic process, fermentation. Something is wrong with it. One catabolic process is fermentation. Is a partial degradation. Fermentation is partial degradation of sugars and other organic fuel that occurs without the use of oxygen, of course. However, the most efficient catabolic pathway is aerobic respiration. Most efficient because it makes use of in which oxygen is consumed as a reactant along with the organic fuel. Air, bios, life. Okay. The cells of most eukaryotic and many prokaryotic organisms can carry out aerobic respiration. Some prokaryotes use substances other than oxygen as reactants in similar process that harvest chemical energy without oxygen. This process is called anaerobic respiration. Technically, the term cellular respiration includes both aerobic and anaerobic. However, it originates as a synonym for aerobic respiration because of the relationship of that process to organismal respiration, in which an animal breathes in oxygen. Thus, cellular respiration often used to refer to the aerobic process. Although very different in mechanism, aerobic respiration is in principle similar to the combustion of gasoline in an automobile engine after oxygen is mixed with the fuel. Food provides the fuel for respiration and exhaust, blah blah blah. Carbohydrates, fat, proteins from food can all be processed and consumed as food. In animal diets, a major source of carbohydrates is starch. A storage, polysaccharides that can be broken down to glucose subunits. Here we will learn the steps. So these are the steps. ATP. Now, this breakdown of glucose is exergonic, having a free energy change of minus this number per mole of glucose decomposed. Recall that negative energy indicates that the products of the chemical process store less energy than the reactants. So the reactants had more stored potential energy, and that the reactants can happen spontaneously without an input of energy. Catabolic pathway do not indirectly move flagella, pump solutes across membranes, polymerize monomers, or perform other cellular work. Catabolism is linked to work by a chemical drive shaft, which is the ATP, adenosine triphosphate. Now, to keep working, the cell must regenerate its supply of ATP from ADP. To understand how cellular respiration accomplishes this, let's examine the fundamental chemical processes known as oxidation and reduction. Redox reactions, oxidation and reduction, how do the catabolic pathways that decompose glucose and other organic fuels yield energy? The answer is based on the transfer of electrons during the chemical reactions. The relocation of the electrons releases energy stored in organic molecules. See, relocation releases, and this energy ultimately is used to synthesize ATP. The principle of reduction and oxidation. In many chemical reactions, there is a transfer of one or more electrons from one reactant to another. These electron transfers are called oxidation-reduction reactions or redox reactions. In a redox reaction, the loss of electron from one substance is called oxidation, and the addition of electrons to another substance is called reduction. When you add an electron, it's charge minus, to another substance, its charge is less, becomes more minus, meaning is reduced. That's the origin of the word. Adding electrons is called reduction, which is this. Adding negatively charged electrons reduces the amount of positive energy or increases the amount of negative energy it has. To take a simple non-biological example, consider the reaction between the element sodium and chlorine that forms stable salt. We could generalize the redox reaction this way. Okay, now in the generalized reaction, substance X electron, the electron donor, which is the reducing agent. Why is it reducing agent? Because it's providing the electron, which it reduces Y, which accepts the donated electron. Substance Y, the electron acceptor, is an oxidative or oxidizing agent. It oxidizes E, as in it removing its electron, takes its electron. Because an electron transfer requires both an electron donor and an acceptor, oxidation and reduction always go hand in hand. Not all redox reactions involve the complete transfer of electrons from one substance to another, though. Not all, of course. Some change the degree of electron sharing in covalent bonds. Because there are covalent bonds and electrons are already shared between them, but the reducing effect of one substance on another will be that it will draw the electron towards it. It will decrease the affinity of that substance to electrons, meaning that the covalent bond will be leaning more towards the reducing the oxidizing agent, sorry, because yeah, exactly, more, because because of the reducing agent. The reducing agent, it will give more electrical affinity to the oxidizing agent, to the reduced substance, and that is also a redox reaction. That's a very important idea. I mean, I didn't know that before. Good. Okay. Now, methane combustion is an example. The covalent electrons in methane are shared nearly equally between the bonded atoms, because carbon and hydrogen have about the same affinity for valence and shared electrons. They're about equally electronegative, exactly. But when methane reacts with O2, forming CO2, electrons end up shared less equally between the carbon atom and its new covalent partner. The oxygen atoms, which are very electronegative, in effect, the carbon atom has partially lost its shared electrons. Partially lost. So it was oxidized. Thus methane was oxidized by the oxidizing agent, which is O2. Now let's examine the fate of the reactant O2. O2 was reduced. The two atoms, meaning they increase their electric charge, share their electrons equally after the oxygen is bonded to two H atoms in H2O. The electrons of those covalent bonds spend more time near the oxygen. Each oxygen atom has partially gained electrons, partially. So the oxygen molecules has been reduced because the oxygen atom is so electronegative. O2 is one of the most powerful of oxidizing agents. Why? Because it's so electronegative. Because of the electronegativity of oxygen as an atom. Now, energy must be added to pull an electron away from an atom, just as energy is required to push a ball uphill. The more electronegative the atom, the stronger its pull on electrons. The more energy is required to take an electron away from it. An electron loses potential energy when it shifts from a less electronegative atom towards a more electronegative atom. Why is that? Simple. Important idea. It loses its potential energy when it shifts from a less electronegative towards a more electronegative. When the electron, in a redox reaction, in a reduction oxidation reaction, the electron moves from one atom to another based on multiple factors. Let's say for instance oxygen. So oxygen has a high electronegativity. Oxygen will oxidize a substance. Oxidizing a substance means it will it will grab an electrons from it, or partially increase its electronegativity. Meaning, let's say let's forget about the partially and stuff. So it will oxidize an agent and be reduced itself, meaning it will gain more electronegativity. Now, oxygen has high electronegativity, and when an electron moves from a lower electronegative atom to a high electronegative atom, it loses energy or potential energy. That is why originally this molecule was a strong reducing agent, because its electrons have a high potential energy. That's why they're able to move from this reducing agent to the will be reduced agent. Now, I think going further into explaining why and such, it will be outside the required material. So a redox reaction that moves the electron closer to an oxygen atom, such as the burning of methane, therefore releases chemical energy and releases the chemical energy. Where was that chemical energy? It was stored as potential energy in the electron of the oxidized substance, of the reducing agent, the molecule that's ready to provide the electron to another. Whoops. See what's in here. Methane combustion as an energy yielding redox reaction. It's basically what we explained. The reaction releases energy to the surroundings because the electrons lose potential energy when they end up being shared unequally, spending more time near electronegative atoms such as oxygen. Reactants here, like methane, oxygen. Now the products. Now methane is gonna be reduced. It's gonna be oxidized by oxygen. Oxygen is gonna be reduced by methane. Oxygen will have more electronegativity, meaning compared to its original form. So to explain this, here previously we had oxygen, covalent bonds. Electrons were shared almost equally between the two oxygen atoms. So oxygen had this particular electronegativity. C, carbon, with H, it shared electrons, let's say at a specific spot closer to it. It was more electronegative. In CO2 and in H2O, here O with H, I think I'm not sure though. I think no, just like that. Electrons are going to be closer to oxygen, meaning its electronegativity was increased, meaning the electrons from methane moved to a substance with higher electronegativity. Now oxygen now has higher electronegativity. It was reduced, just like in here as well as in here. Oops. Carbon here. When carbon moved to oxygen as CO2, its electronegativity no. It was oxidized, meaning it lost charge, or its electronegativity was reduced in favor of oxygen, which electronegativity increased with the H, increased with the O. And that's just it, basically. So much ado for nonsense. Now, got it. Oxidation of organic fuel molecules during cellular respiration. Which is the specific ideas that we need here. The oxidation of methane by oxygen is the main combustion reaction that occurs at the burner of a gas stove. The combustion of gasoline. Can you just get into the point? Examine again the summary equation for cellular respiration, but this time think of it as a redox process. Okay. Oxidizing agent. Oxidized will be oxidized. The release of energy by electrons moving from a molecule or a bond with less electronegativity to more electronegativity. Yeah. It loses potential energy, which is transformed into chemical energy here. Oxygen is going to be reduced, more electronegativity here. It will be reduced by attracting the electrons in its this and that closer to it. Electrons will become more stable in a substance with more electronegativity, right? Which is as in the combustion of methane, the fuel is oxidized. Now, this is an important idea. Why do organic molecules matter so much? As why are they one of the most efficient sources of fuel, excellent fuel? Because of their abundance of hydrogen, and the bonds of hydrogen within the molecules, their bonds are a source of the hilltop electrons, whose energy may be released as these electrons fall an energy gradient during their transfer to oxygen from high energy electron that is more volatile, that is more ready to move, to a more attractor, which is the oxidizing agent, which is oxygen. The summary equation for respiration indicates that hydrogen is transferred from glucose to the oxygen atoms in O2. But the important point, not visible in the summary, the energy state of the electron changes as hydrogen is transferred to oxygen. Now, the whole focus of the original root source of how cellular respiration provides energy is the energy of the electron, and it's called energy state. It changes when hydrogen is transferred to oxygen from the organic fuel, from the organic molecule. In respiration, the oxidation of glucose, I hate this, transfers electrons to a lower energy state. Now, the electron had energy. These electrons had energy. So what happened to that energy? It was liberated. That becomes available for ATP synthesis from ADP and inorganic phosphate. So in general, we see fuels with multiple CH bonds oxidize into products with multiple CO bonds. The main energy yielding food, these are the main energy yielding food, carbohydrates and fat are reservoirs of electrons associated with hydrogen, often in the form of CH bonds. Only the barrier of activation energy, remember the barrier of activation energy holds back the flood of electrons to a lower energy state. Without this barrier, a food substance like glucose would combine almost instantaneously with oxygen. If we supply the activation energy by igniting glucose, it burns in air, releasing this amount of energy of heat per mole per glucose. Body temperature is not high enough to bypass that. Instead, if you swallow some glucose, enzymes in your cell will lower the barrier of activation energy, allowing the sugar to be oxidized and provide energy. The steps. Now, this stepwise energy harvest, the NAD plus and the electron transport chain. NAD plus, electron transport chain. If energy is released from fuel all at once, it cannot be harnessed efficiently for constructive work. For example, if a gasoline tank explodes, it's going to drive a car very far. Cellular respiration does not oxidize glucose or any other fuel in a single explosive step either. Rather, glucose is broken down in a series of steps, each one catalyzed by an enzyme. At key steps, electrons are stripped from the glucose. As is often the case in oxidation reaction, each electron travels with a proton, which is H, thus a hydrogen atom. The hydrogen atoms are not transferred directly to oxygen, but instead are usually passed first to an electron carrier, which is the NAD, a coenzyme called nicotine amide adenine dinucleotide. Nicotine diamine. So it's not nicotine, NAD, nicotine amide adenine dinucleotide. What does that mean? That means it has double nucleotide bases. It has adenine and the nicotine amide component attached to, I would guess, probably to the nucleotide, to the so there's an like adenine and nicotine amide nicotine amide adenine dinucleotide. It's a derivative of the vitamin and vitamins are coenzymes. Niacin. Niacin. This coenzyme is well suited as an electron carrier. Why? Why is that? Because it can cycle easily between its oxidized form, NAD+, and its reduced form, NADH. When it's in the oxidized form, meaning it's robbed of its electron, it can cycle to a NADH, carry the electron with its proton as a hydrogen atom to deliver it elsewhere. So, in order for it to carry the electron, it will be the electron acceptor. We can notice that it's an NAD plus, positively charged. It functions as an oxidizing agent, just like oxygen, during respiration. Now, how does NAD plus trap? How does it trap electrons from glucose and other organic molecules in food? We have other enzymes called dehydrogenases. D, from its name, it like robs the glucose from its hydrogens. Dehydrogenases remove a pair of hydrogen atoms, meaning 2 electrons, 2 protons, and two from a substrate, which is like glucose, for example, thereby oxidizing it. The enzyme delivers the 2 electrons along with 1 proton to its coenzyme. Delivers it to the NAD+, forming NADH. Now we still have the other proton. So why 2 electrons and 1 proton, meaning 1H, 2 electrons, or 1H and 1 electron? That can be shown here as NAD plus, which is nicotinamide adenine dinucleotide, is positively charged. So 1 electron would turn it into would neutralize it, and you can just add H. It will readily accept it. The other proton is released as a hydrogen ion, H+, into the surrounding solution. So we have glucose, we have NAD+ as a coenzyme, dehydrogenase, the enzyme, will do this basically. By receiving 2 negatively charged electrons but only 1 positively charged, we just mentioned this proton, the nicotinamide portion of NAD, the nicotinamide portion of NAD+ has its charge neutralized when NAD+ is reduced to NADH. The name NADH shows the hydrogen has been received in the reaction. NAD+ is the most versatile electron acceptor in cellular respiration and functions in several redox steps. Electrons lose very little of their potential energy when they are transferred. They lose very little when they are transferred from glucose to NAD+. Because they have similar electronegativity, basically. Each NADH molecule formed during respiration represents stored energy. It's the same energy that was in glucose that can be tapped to make ATP. But it's more readily available to be chemically grabbed or tapped. To complete the fall down, an energy gradient from NADH2O2. How do electrons that are extracted from glucose and stored as potential energy in NADH finally reach oxygen? It will help to compare the redox reaction, more analogies, to a much simpler reaction, the reaction between hydrogen and oxygen to form water. Mix H2 and O2, provide a spark of activation energy, and the gases combine explosively. In fact, the combustion of liquid hydrogen and oxygen is harnessed to power the rocket engines that push satellites into orbit and launch spacecraft. The explosion represents the release of energy as electrons of hydrogen fall closer to the electronegative oxygen atoms. Cellular respiration also brings hydrogen and oxygen together to form water. Yeah. But there are two important differences. They're not explosives, they're multi-step. The hydrogen that reacts with oxygen is derived from organic molecules rather than directly. Second, instead of occurring in one explosive reaction, respiration uses an electron transport chain to break the fall of electrons to oxygen to several energy releasing steps. See the figure here? Oh, this is the NADH. NAD plus. Here. Hey, what was? NAD plus is, we have here nicotinamide oxidized form. No, nicotinamide. The first prime oxidized form means without H. Not plus, yeah. Why this is the NAD plus in its oxidized form. First prime, 2, 3, 4, and I think 1, 2. Anyway, we get this. It's nicotinamide. This is the nicotinamide. This adenine, which is nucleotide. So if you look at it here, the nucleotide, well, nucleotide and nucleotide. Connected by phosphate groups. NAD. And that's just it. Okay, nicotinamide. It has amide here. From the vitamin niacin. And plus. Why is this the N plus though? Yeah. Which is okay. This is the adenine group. Okay, let's just dinucleotide. So one nucleotide has adenine, one nucleotide has nicotinamide. Okay, that's why it was called nicotinamide, adenine, dinucleotide. Interesting. So it's just the nicotinamide that does the whole thing. Okay. So if we look at the other side, okay, it's gonna connect two H's here, and N is no longer positively charged, it's neutralized, and there is a release of an H plus, which is what they call it. They call it release of hydrogen ion. Okay, good. Now the electron transport, it's called an electron transport chain for a reason. It consists of a number of molecules, mostly proteins, built into the inner membrane of the mitochondria of eukaryotic cells, of course, and for respiring prokaryotic cells in the plasma membrane. If we maybe do this. Why is it? Plasma membrane and mitochondria in the inner membrane of mitochondria in prokaryotic cells. Electrons are removed from glucose, are shuttled by NADH electrons, all of them, to the top, which is the higher energy end of the chain. At the bottom, the lower energy end, O2 captures these electrons along with the straggler hydrogen nuclei. Think, forming water. Anaerobically, respiring prokaryotes have an electron acceptor at the end of the chain that is different from oxygen, like sulfide or something like that. Electron transference from NADH to oxygen is an hexagonic reaction, and with a free energy of minus 53 calorie per mole, minus 22 joule. So yeah, minus 53 kilocalorie per mole. Instead of this energy being released and wasted in a single explosive step, electrons cascade down the chain from one carrier molecule to the next in a series of redox reactions, losing a small amount of energy with each step, and they finally reach oxygen. The terminal electron receptor, which is oxygen, which has a very great affinity for electrons. Each downhill carrier has a greater affinity for electrons. Like each lower step until you reach the final boss, which is oxygen. That's right. Final. Final boss of electronegativity has greater affinity for electrons than and is thus capable of accepting electrons from oxidizing its uphill part with oxygen at the bottom of the chain. Now, therefore, the electrons transfer from glucose to NAD plus, reducing it to NADH, fall down in energy gradient in electron far more stable locations in the electronegatively negative oxygen atom from O2. Put another way, oxygen pulls electrons down the chain in energy-eating tumble analogous to gravity pulling objects downhill. In summary, during cellular respiration, most electrons travel the following downhill route: glucose, NADH, electron transport chain, oxygen. Basically, yeah. Hey. Later in this chapter, you will learn more about how cell uses energy released from the For now, having covered the basic physics mechanism of cellular respiration, let's look at the entire process by which energy harvest. Okay, now the stages of cellular respiration. A preview. The harvesting of energy from glucose by cellular respiration is a cumulative function of three metabolic stages. We list them here along with color-coded coding scheme we will use throughout the thing. Okay. Glycolysis. Huh? Glycolysis. Oh, glycolysis. Color blue. Pyruvate oxidation, light orange. Citric acid cycle, dark orange. Oxidative phosphorylation, electron transport, and chemiosmosis, purple. Biochemists usually reserve the term cellular respiration, interesting, for stage 2 and 3 together. In this text, however, we include glycolysis as part of the cellular respiration because most respiring cells deriving energy from glucose use glycolysis to produce the starting material for the citric acid cycle. Introduction to electron transport chains. An uncontrolled reaction. One step, release of explosive energy. Cellular step, multi-step. No, whatever. Why is there like a big ass explanation? Glycolysis and then pyruvate oxidation are the catabolic pathways that break down glucose and other organic fuels. Glycolysis, which occurs in the cytosol. Okay. What colors to use? Blue? Okay, we can use blue. Let's use blue. So glycolysis in the cytosol begins the degradation process by breaking glucose into two molecules of pyruvate. In eukaryotes, pyruvate enters the mitochondrion and is oxidized to a compound called acetyl-CoA, which enters the citric acid cycle. So light orange. What's a light orange? This is orange. Orange? No. This. What is orange? Fuck. This is yellow. This is orange. Can I just get a normal color choosing this? Pyruvate enters the mitochondria, oxidized to a compound called acetyl-CoA, and it enters the citric acid cycle. Dark. This, whatever. The citric acid cycle. There, the breakdown of glucose to carbon dioxide is completed. Joy. In prokaryotes and the cytosol. Okay, and after oxidative phosphorylation, just pink. This pink. Thus, the carbon dioxide produced by respiration represents fragments of oxidized organic molecules. Some of the steps of glycolysis and the citric acid cycle are redox reactions. Some of them are redox reactions which dehydrogenases transfer electrons from substrates to NAD+, or the related electron carrier, flavine adenoside dinucleotide, forming NADH or NAD or FADH2. We will learn more about FAD and FADH2. In the third stage of respiration, the electron transport chains accepts the electrons from NADH to FAD or FADH plus. They accept them from NAD and FADH plus generated during the first two stages and passes these electrons down the chain. At the end of the chain, the electrons are combined. At the end, they are combined with molecular oxygen, the final boss, and hydrogen ions, forming water. The energy released at each step of the chain is stored in a form of the mitochondrion. Is stored in a form the mitochondrion can use to make ATP from ADP. or cytosol like prokaryotic cells. This mode of ATP synthesis is called oxidative. This mode is called oxidative phosphorylation because it's powered by the redox reaction of the electrons transport chain. It's called oxidative phosphorylation because this is how ATP is made from ADP. From ADP, which is called oxidative phosphorylation. Now, in eukaryotic cells, the inner membrane of the mitochondrion is the site of electron transport and another process called this is important. In eukaryotic cells, the inner membrane inner membrane of the mitochondrion is the site of the electron transport. And another process called chemiosis together making up oxidative phosphorylation. In prokaryotes, these processes take place in the plasma, inner plasma membrane, whatever. In prokaryotes, plasma membrane. Oxidative phosphorylation accounts for almost 90% of ATP generated by respiration. A smaller amount of ATP is formed directly in a few reactions of glycolysis and the citric acid in glycolysis and the citric acid cycle by a mechanism called substrate level phosphorylation. So it's not an overall oxidative, it's substrate level phosphorylation. This mode of ATP synthesis occurs when an enzyme, when does it happen? Why does it happen? How does it happen? When an enzyme transfers a phosphate group from a substrate molecule to the ADP, rather than adding an inorganic phosphate to ADP as in oxidative phosphorylation. So, in oxidative phosphorylation, there is an inorganic phosphate next to the ADP. However, in this substrate level phosphorylation, a whole phosphate group is added directly to the ADP. That's the idea here. Substrate molecule here refers to an organic molecule generated as an intermediary during the catabolism of glucose. So it's just an organic molecule as an intermediate in the thing, which is when an enzyme, right? Yeah. You'll see examples of substrate level phosphorylation later in the chapter in both glycolysis and the citric acid cycle. You can think of the whole process this way. When you withdraw, more analogies, I hate analogies. When you withdraw a relatively large sum of money from an ATM, it's not delivered to you in a single bill or a large denomination. Instead, the machine dispenses a number of smaller denomination bills that dispenses smaller amount. This is analogous to ATP production during cellular respiration. For each molecule of glucose degraded to CO2, the cell makes up about 30. Okay. For each, this is a good information. For each, so 1 molecule of glucose, we get about 32 of ATP. And we know that each ATP has a stored 7.37 0.3 of free energy. Respiration نتذكرها. Respiration cashes in the large denomination of energy banked in a single molecule of glucose, which is 32 by this number, for the small change of many molecules of ATP, which is more practical for the cell to spend on its work. This preview has introduced you to how glycolysis, strict cycle oxidative phosphorylation fit into the process of cellular respiration, so you can keep the big picture in mind. As you read about the chemical reactions, remember that each reaction is catalyzed by a specific enzyme, some of which are in the figure 7.3.2. It's a good introduction. Concept check. Goodbye, concept check. Now we start with glycolysis.